This is our final video for the semester. We move on to chapter 24, which looks at nuclear reactions and some of their applications. Let's start off with a comparison of chemical reactions to nuclear reactions. As you've come to learn throughout this year, in a chemical reaction, one substance is converted into another, but the individual atoms never change their identities. In nuclear reactions, atoms of one element typically are converted into atoms of another element. In chemical reactions, electrons are involved in bond breaking and bond formation, but the nuclei do not take part. In a nuclear process, the protons, neutrons, and other nuclear particles are involved, and electrons take part much less often. In a chemical reaction, reactions are accompanied by relatively small changes in energy, maybe tens to hundreds of kilojoules per mole, and maybe for the highest energy ionic bond breaking 1,000 kilojoules per mole. And there are no measurable mass changes in the atoms themselves. In nuclear transformations, we see reactions are accompanied by very large energy changes, which can be on the order of billions of kilojoules per mole, and the mass changes are measurable. In chemical reactions, we see that the rates are typically influenced by temperature, concentration of reactants and sometimes products, the presence of catalysts, and the chemical environment in which an element occurs. For nuclear processes, the reaction rate depends on the number of nuclei, as we'll see, but they're typically not affected by temperature, by catalysts, and only very rarely by the chemical environment in which an element occurs. Let's go look at the nucleus. We know that the atom's mass is primarily concentrated in the dense, small nucleus at the center of the atom. The nucleus is composed of neutrons and protons, which we collectively call nucleons. Thus, the total number of nucleons in a nucleus is equal to the mass number for that nucleus. A nuclide is a nucleus with a given composition. Each isotope of an element has a different nuclide. A nuclide is often designated by a mass number, so for example, chlorine-35 and chlorine-37. The relative mass and charge of the particle is often described by the following notation, the A, Z, and X notation, where X is the particle, A is the mass number, and Z is the charge of the particle. For the individual subatomic particles we've looked at this semester, then, we would use this nomenclature as follows. For electrons, they have a mass number of 0, a charge of -1. A proton has a mass number of 1 and a charge of 1. And a neutron has a mass number of 1 and a charge of 0. Next, let's look at radioactivity. Stable nuclei remain intact indefinitely, and the vast majority of nuclei that we've looked at this semester are just that, stable nuclei that remain intact. But it turns out that most of the nuclei that we have discovered are actually unstable. Unstable nuclei exhibit radioactivity. That is, the spontaneous disintegration of a nucleus by radioactive decay that's not affected by temperature, pressure, or the chemical environment. Nuclides decay, and when they do, they emit radiation, and they change into nuclides of a different element. Here we see the three common types of radioactive emission. There are emission of alpha particles, which really are simply helium nuclei, but with high energy, so 2 protons and 2 neutrons. There are beta particles, which are simply high-speed electrons. These speeds can be up to near to the speed of light. And finally, we have gamma rays, which are simply high-energy photons. They're very high energy photons beyond what we've encountered this semester. higher energy than even X-rays. Now, if you look in the lower right-hand figure here, you see something that is reminiscent of Thomson's cathode ray experiment. We have a radioactive material, and then we have electric field, so we have a positive and a negative electrodes, and then we have a phosphorescent screen at a distance. As the particles pass through, they can be affected by the electric field. Alpha particles are attracted to the negative electrode, and then they'll appear on the screen. Beta particles are affected and attracted to the positive electrode. And finally, gamma particles, or gamma rays, which have no mass and no charge, they pass straight through the electric field. For each of the types of radioactive emissions, we can look at their penetrating power. Penetrating power is the ability of the radioactive particles to pass through substances. We find out that the penetrating power of a radioactive emission is inversely related to the mass or the charge of the radioactive emission, and it's directly proportional to the energy of the emission. So, particles with large mass and charge do not penetrate very deeply, but higher energy particles will penetrate more deeply. So we see here, we can compare alpha, beta, and gamma particles, and the three types of particles here are passing through paper. So the alpha particle will be stopped by paper because of its large mass and its high charge. It will interact with the paper structure. Beta particles will typically pass right through paper, and gamma particles pass through paper. Now, as these move on, beta particles will typically interact much more strongly with aluminum. If you remember back to Thomson's electron diffraction experiments, you know that electrons are affected by the aluminum crystal lattice, and beta particles are slowed down substantially, and depending on the thickness of the aluminum, they can be stopped completely. Gamma particles pass right through aluminum, but they'll interact with lead or very large, massive, dense structures, and they'll be eventually stopped by those structures. So you can see that gamma particles are the most penetrating, beta particles next, and then alpha particles are the least penetrating. These penetration effects can be used in various applications. We're not going to discuss applications extensively in this video. Your textbook will discuss them, and if you're interested, you should read those. In particular, the textbook covers a lot on biological applications. But here we'll just look at this basic concept of penetration. So first we have something called radiation therapy. So in radiation therapy, you introduce a radioactive source to kill cancer cells. So you might think, well, you're going to need penetrating radiation, so will alpha particles work? Well, they actually do work, because you can make a radioactive nucleus that will become an alpha emitter, and you can introduce that into a molecule, and that molecule can target a particular organ within the body. And then that drug is injected into the body, goes to that location where the tumor is located, and then the alpha particles will decay and can kill the tumor. Cancer cells divide more rapidly than do normal cells, and therefore they're susceptible to radioisotopes, which will interfere with their cell division and kill them. Ionizing radiation can also be used to destroy microbes, and this is commonly used for irradiating food, particularly fruit and vegetables, and can significantly increase the shelf life of these by killing microorganisms. Most often, fruits and vegetables are exposed to gamma radiation because that will penetrate the food, having very little effect on the food, but there'll be interaction with the microorganisms and it will cause them to die. So that'll allow the food to to stay fresh longer. So in the lower right-hand corner, you see peaches that have been irradiated by gamma radiation, and those that have not. The ones that have been irradiated stay good longer. Sometimes beta radiation is also used. This can also be used, ionizing radiation can also be used for insect control. So for example, if you have grains and there's potentially insects present, if these are being transported, you can expose these to radiation to kill the insects. And you can also use ionizing radiation as a high energy density source for example, spacecraft missions where you're going to be traveling a long way and you can't take along a very large, heavy energy source. Next, we're going to look at nuclear equations, just like we looked at chemical equations throughout the year. So when nuclides decay, they form product, or sometimes termed daughter nuclides, of lower energy. Things go to lower energy, more stable systems. The excess energy is carried off by the emitted radiation and the recoiled nucleus of the daughter nuclide. The decay process is represented by a balanced nuclear equation, and both charge and total mass has to be balanced between the reactants and the products. Now we're going to look at the common types of decay processes that nuclides undergo. The first one is alpha decay. Alpha decay involves the loss of an alpha particle from the nucleus. So for each alpha particle emitted, the mass number will drop by 4, and the nuclear charge drops by 2, because 4 nucleons, and 2 of those are protons. This is the most common form of decay for heavier nuclei, particularly heavy unstable nuclei. So here we see radium, and radium-226 will decay to form radon-222 plus the alpha particle. Next, we have beta decay. This involves the ejection of a beta particle from the nucleus. And you might think, well, where does an electron come from the nucleus? Well, a neutron in certain nuclear decay processes is converted into a proton, which remains in the nucleus, and the electron is expelled. So the neutron converts into a proton and a beta particle or electron, and the high-speed electron is emitted. In this case, the mass number remains the same in the daughter nuclide, but the nuclear charge now increases by 1 unit because we've converted a neutron into a proton. Here we see nickel-63, which is a beta emitter, and it converts into copper-63 plus our beta particle. Next, we have something called positron emission, which is the emission of a positron particle from the nucleus. This is the first time we've encountered that this year. A positron is the antiparticle of an electron, which has the same mass as an electron, but a positive charge. A proton in the nucleus, in positron emission, converts into a neutron, and a positron is emitted in this case. So here we see a proton converts to a neutron, and a positron comes out. Thus, the mass number remains the same, but our nuclear charge decreases by 1 since we've lost a proton. So here we can see as an example, carbon-11 converts to boron-11 plus the emission of a positron. Electron capture is our next type of decay process. This occurs when a nucleus captures an electron in one of the low-lying atomic energy levels, what we might have termed a core electron earlier this year. So the nucleus captures a core electron, and then a proton is transformed into a neutron. So the proton captures the electron and converts to a neutron. The effect on A and Z is just the same as for a positron emission. So our A value remains the same, but we see that the nuclear charge decreases by 1 unit. So here we see iron 55 capturing an electron to form manganese 55, with the emission of a high energy photon. Next, we have gamma emission. Gamma emission involves radiation of very high energies. So these are high energy photons, higher in energy than X-rays. Gamma emission usually occurs together with other forms of radioactive decay. Several gamma photons of different energies can be emitted from an excited nucleus as it returns to the ground state, so we can see multiple emissions from a single process. Gamma emission results in no change in the mass number or the nuclear charge, since gamma rays do not have mass, nor do they have charge. Now we'll look at a summary table for the various types of radioactive decay. We have our alpha decay, which emits an alpha particle, and we can see that our mass number decreases, our nuclear charge decreases, and number of neutrons decreases. Beta emission involves no change in mass number, but an increase in our nuclear charge and a decrease in the number of neutrons. Positron emission, similarly, we see no change in mass number, but here we see the nuclear charge drop by 1 and our number of neutrons increase by 1. Electron capture behaves like positron emission, where we have no change in our mass number, but a decrease in our nuclear charge and an increase in the number of neutrons. And finally, gamma emission, which does not change any of our nuclear particles, but is just an emission process of the excited or high energy nuclear structure going to a lower energy, but keeping the same nucleons present. This table summarizes the various changes in A and Z for our various modes of decay: alpha, beta, positron, electron capture, and gamma emission. These will all play an important role as we think about the various transformations that nuclei will undergo. Next, let's think about nuclear stability. So we know that there are many nuclei that are truly stable. They do not seem to undergo any sort of decay on any time scale that is observable. So, for example, carbon-12. Carbon-12 is a stable nucleus. But there are other nuclei that are unstable. There are two key factors that determine the stability of a nuclide. First, the number of neutrons, the number of protons, and their ratio, the ratio of neutrons to protons, determines stability. Also, the total mass of the nuclide determines its stability. And this can be seen by a graph that we're going to look at in just a moment that plots the number of neutrons as a function of the number of protons for all of the stable nuclides. And it produces what we call a band of stability. So the band of stability represents those nuclides which are stable. Now, at low values, we find that nuclides are typically stable when the number of protons, the number of neutrons are roughly the same. But as the total charge of the nucleus goes up, as the mass number for the system goes up as well, we find that the ratio of neutrons to protons goes up for stable nuclei. And then we find out that all nuclides with Z values greater than or equal to 83 are unstable. Now, your textbook says greater than 83, but it turns out that the nuclide 83, which is bismuth, was, in the last couple of decades observed to be unstable, but it's unstable to the tune of something that's on the order of 100 times, or actually more than that, times the much not 100 times, but much longer than the lifetime of the universe that we currently estimate. But it's still very stable. So bismuth, it's found in Pepto-Bismol, and so it's a stable, for our purposes, it is a stable nucleus. But from a physicist's point of view, it's been found to be strictly, it is unstable. So we find out that lead is the largest truly stable nucleus. So here's our plot of number of neutrons versus number of protons for all the nuclei that we observe to be stable. So we've got a straight line here, the n over z equals 1 value, and you can see at low values for number of protons, the ratio of n over z is close to 1. But as the value of the number of protons increases, we need more and more neutrons to stabilize the nucleus. And we'll see why in a little bit, but of course, as we have more protons, we have more more electrostatic repulsion between those protons, so we need more neutrons to provide strong nuclear force to hold the nuclei together. And this shows all the stable nuclei up to bismuth 209, which, as we said before, has been observed to be strictly unstable, but for our purposes as chemists, it truly is a stable nucleus on our time scale. Now, what we notice here, if you look on the right-hand side, you see that the black dots represent the stable isotopes or the stable nuclides. The blue dots are those nuclides which undergo decay by beta emission. And then the green dots are ones that undergo decay by positron emission or electron capture. And then the red nuclides are the ones that undergo alpha decay. Before we go any further, I want to take a very short and kind of brief foray into where our elements come from. So, of course, on Earth, we have this nice array of hydrogen and oxygen. Those are our most abundant elements. We've got lots of aluminum and silicon, and there are many other elements that we encounter and use on Earth all the time. But the question comes about, where do these elements come from? And we have evidence that supports something called stellar nucleosynthesis. And I'll show you the model here and then briefly discuss why physicists think this is the best description or best explanation for the source of elements in the universe. So we start off with cosmic dust, which over very long time scales through gravitational electrostatic interactions will coalesce into cosmic dust, which can coalesce into particles, which can build into sort of heavenly bodies, into planets and into stars ultimately, right? And other sorts of structures in the universe. And if the mass of the structure is large enough, the gravity can start to pull this in, and as it pulls, the energy associated with that gravitational attraction can heat up the system such that hydrogen begins to what a nuclear physicist would call burning. Now, it's not combustion as we know it, it's a nuclear process where hydrogen begins fusing and forming and transforming into helium. Now, in our solar system, we have a couple of our two biggest planets appear to have coalesced in a similar manner, but they're simply small enough that they never were able to continue on to this nuclear fusion process. But our sun, of course, does fuse and forms helium. Now, for larger systems, larger stars, the helium, as the lifetime of the star continues on, the gravitational force continues, and the star can begin heating and proceed through a series of burning processes where helium then can move on to form heavier nuclei. For example, carbon-12, oxygen-16, neon, magnesium. And ultimately then, red supergiant core begins to burn, and carbon and oxygen will begin to undergo what we'll see as fusion and can form elements all the way up to iron 56 and nickel 58. And that's typically the largest nuclei that actually, the largest atoms that will form inside of a star. But when the star begins to, when the star explodes, it leaves behind a neutron star, and then there's a whole lot of neutrons that are released from the neutron star, and the atoms that are around this exploding supergiant can capture those neutrons to form larger nuclei. So this is the source of things in the second and third rows of the periodic table, the lanthanides, and on Earth, for example, the actinides up through uranium. There are some other processes that have been observed, and recently two neutron stars were observed colliding, and their gravitational wave that was produced from the event was observed. And what was seen was atomic emission coming from this interaction, and the atomic emission could show the elements that were produced. So what we can do is we can look at these red supergiants and we can see the atomic emissions for these various elements that are produced within the red supergiant. And that contrasts with what you see from stars that don't form these sorts of systems. And what's very interesting is, you remember in the middle of our periodic table is an element, technetium, which we don't really talk about much because it has no stable nuclei. It's only radioactive. But in these neutron sort of bursts that come out, we see technetium emission. And we know technetium could not have been around for the lifetime of the star. And so we can see that kind of helps us to understand that this neutron capture process during this explosion is where these heavier elements come from. And here's a picture of a star with the various levels of or regions where fusion occurs to form the various nuclei. But moving on now, we can go back and look at our nuclear structure again. And we see that protons in the nucleus, of course, experience very strong electrostatic repulsive forces, but they're still held together. And they're held together by the strong force, which exists between all nucleons, and it counteracts the weaker repulsive electrostatic force at very short distances. Of course, the strong force only works at very short distances. At longer distances, the electrostatic interactions, the Coulomb repulsions, completely dominate. And those are the ones we see in chemistry. But in nuclei, for very short distances within the nucleus, the strong force becomes dominant. Nucleons are found in nucleon energy levels, just like we find electrons in electron energy levels in atoms. And pairing of spins, like nucleons, leads to greater stability. And so what we find is, for these various nuclear structures, elements that have an even nuclear charge typically have a larger number of stable nuclides. We find that over half of the stable nuclides that are known have both an even number of neutrons and an even number of protons. Another thing that's interesting is we find that nuclides that have a number of neutrons or a number of protons that is equal to either 2, 8, 20, 28, 50, or 82, and ultimately 126, these are found to be exceptionally stable. And for nuclides, these are called magic numbers, and they're thought to correspond to the number of protons or neutrons to fill nucleon energy levels. So what you see is with the nucleus, it's very similar to electronic structure. Remember, think back to the electronic structure we learned about. If we have 2 electrons, we fill the 1s level. If we have another 10 electrons, we fill the 2s2 and the 2p6. So that would be 8 electrons there for a total of 10. So the 1s2, 2s2, and 2p6. And of course, you can fill up a D level and fill up an F level. And so you find that certain numbers of electron counts are particularly stable, like for our noble gases. The same thing goes for nuclides. There are simply magic numbers where you fill up the available energy levels to make particularly stable structures. Now here's an odd even breakdown on our stable nuclides. So the table on the top shows the number of stable nuclides that exist. So if we have an even number of protons and an even number of neutrons, there are 157 different nuclides that are stable. If we have an even number of protons and an odd number of neutrons, there are 53 nuclides that are stable. If we have an odd number of protons and an even number of neutrons, there are 50. But the odd number of protons and odd number of neutrons, there's only 4. So you can see nitrogen, there's just a few of these. There's a version of lithium, boron, nitrogen, and of course the proton itself is odd number of protons. And on the lower table, we see for elements 48 to 54, this is just a small subset or sample size. But looking at these elements from cadmium through xenon, we see our atomic number increases from 48 to 54. And you can see in bold the elements that have an even atomic number, they have a larger number of stable nuclides. If they have an odd atomic number, there is a lower number of stable nuclides. So let's look at the nuclides that decay. And these are the common modes of decay. We find that nuclides that are neutron rich, that is, they have too many neutrons, they're way above that stability line in our graph that we looked at earlier. They have a high neutron to Z ratio. These typically decay by beta decay. So a neutron will convert to a proton that lowers the N over Z and pulls it back into a stable region. And in this case, you are converting to an element with a higher atomic number, and you're releasing a beta particle. There are elements that are proton rich. They have too many protons for their nucleus. They lie below the stability band on our graph. So they have a low N to Z ratio. These typically decay by positron emission or by electron capture. So here, a proton converts to a neutron. So we increase the ratio of N over Z to bring it into the stability region. And finally, for our heavy nuclides, those with atomic numbers greater than 83, these decay by alpha emission. And that allows us to reduce both Z and N. So all of our heavy nuclei, uranium, plutonium, protactinium, all of the actinides, these primarily decay initially by alpha decay to reduce both Z and N to pull it back into the stable region. The mode of decay relates to the atomic mass. So the atomic mass of an element is the weighted average of its naturally occurring isotopes. Remember that. We learned that a long time ago in General Chemistry 1. The atomic mass of an element is the weighted average of its naturally occurring isotopes. So for example, carbon has carbon 12 and 13. Carbon 12 is roughly 99%. Carbon 13 is 1%. So the atomic mass is 12.01 grams per mole for isotope averaged carbon. So we have what we know to be the atomic mass of an element. If the mass number A of a stable nuclide is close to the atomic mass, then it's going to be right in the region we expect. So we want our nuclides that are going to be stable to have a mass number that's close to the atomic mass. What about the unstable nuclides? Well, an unstable nuclide for an element, if it has an A value that's significantly more than the atomic mass, what does that mean? It has too many neutrons, and it's probably going to decay by beta emission to bring it back into the stability region. If an unstable nuclide has the A value much less than the atomic mass, that means there's not enough neutrons, then it's proton rich. So it's probably going to decay by positron emission or electron capture. So let's look at an example. Here we have neon. Neon, if you go and look at your periodic table, has an atomic mass of 20.18. So we can look at this table. In the middle, we have three isotopes, neon 20, 21, and 22. Those are all very close to 20. And so those are all stable nuclides. The ones that are below that, neon 17, 18, and 19, these decay by positron emission. And then the ones that are heavier, neon 23 and 24 and higher than that, they decay by beta emission. Now, for very heavy elements, of course, loss of one particle, one radioactive emission, may not be sufficient to get it to a stable nucleus or to a stable nuclide. So here we can look at, for example, uranium-238. Uranium-238 here goes through 13 different intermediate stages before it eventually reaches lead-206 at the very bottom. So you can see we start off with an alpha emission, followed by a couple of beta emissions, followed by a series of alpha emissions, and then a series of competitive alpha and beta emissions. Thus, a parent nuclide may undergo a series of decay steps before a stable product nuclide is formed. This is commonly observed for our heaviest nuclides. Next, we're going to look at the detection and measurement of radioactivity. How do we observe what's going on? We can weigh our samples out. This was often used early on for handling radioactive samples when they were first discovered. Marie Curie, of course, did a lot of work like this. More recently, we have detectors that can detect this emission. And your textbook talks about the first couple, and then I've added in the third one, which is actually a very common way that things are done now. But first off, we have what we call ionization detectors. Sometimes these are called Geiger counters. You may have heard that phrase. These detect radioactive emission because the radiation passes through a gas, and this high energy radiation ionizes the gas as it moves through. So when it ionizes the gas, you get free electrons and their counterpart gaseous cations, and then you can apply a voltage across this gas and collect those charges and measure them. And so this is called a Geiger counter or a Geiger-Müller counter. There's things called a scintillation counter, which detect radioactive emissions by the ability of the radiation to excite atoms, and those excited atoms will emit light, which can be detected by a local phosphorescence or other type of light detector. But there are solid state detectors which can directly detect, for example, gamma emission by the ability to excite atoms within solids. And this is very often seen using, for example, sodium iodide or germanium as the solid. And as the gamma radiation passes through, this is done for something called gamma spectroscopy, you create an electron hole pair, which can be collected by applying a voltage to your solid structure, your sodium iodide or germanium. And these are actually more sensitive detectors than the first couple that we've looked at, and can really give you, in many cases, more information than the upper type of detectors. There's even a type you may hear about sometime called a SILI detector, a lithium drifted silicon. That's more often used for X-rays as opposed to gamma rays. And here we see a picture of a Geiger counter showing the gaseous, inside the circle showing the gaseous argon. Radiation passes through, creating electrons and argon ions, which are collected. And we see amplification and counting of the charges as they go through. The units that are used for radioactivity are shown here. The SI unit is what's called the becquerel, and that is 1 disintegration per second. So it's just simply counting the values. But what happens is a lot of radioactive substances produce very large numbers of becquerels, and so the curie is a more commonly used unit, and the curie is 3.7 times 10 to the 10th decays per second. And very often you'll have things in, for example, microcuries, which would be 10 to the minus 6 of that number. Now we can look at the kinetics for the radioactive decay process. We find that radioactive nuclei decay at a characteristic rate, and it is independent of the chemical environment. Also, the rate of the radioactive decay, which is also called the activity, is proportional to the number of nuclei. And so we can represent this here. The radioactive decay rate A is delta N delta T, and it's equal to K times N, the number of nuclei that are present. That should look very familiar to you from back in our kinetics chapter. That's a first order process, right? So the rate depends on the first order of the concentration. This is a first order process. K then becomes our rate constant. And for nuclear physicists, they call it the decay constant. And so a larger K means we have a higher activity, a higher rate for our process. Radioactivity is typically expressed in specific activity, that is the decay rate per gram of substance, because you're typically not working with a pure radioactive substance. You're dealing with a radioactive substance and very low concentration within some other matrix. So we can go through and look at our integrated rate equations, just like we did back in our kinetics chapter. These are first order processes. And if you remember, half-life was very important for first order processes. That was the only half-life that was independent of the amount of substance, right? So zero order and second order and other order processes, the half-life, which is the time for half the nuclei to decay or for half of our reactive substance to react away, they were all concentration dependent. But for first order processes, the half-life is a constant regardless of the amount of substance we have. So our half-life is the time for half the nuclei in a sample to decay away. The activity will drop by 1/2 with each succeeding half-life. So here we got natural log of NT over N0 is equal to minus KT. That's the integrated rate expression for a first order process. We could rearrange that a variety of different ways, but in the end, the half-life is natural log of 2 divided by K. Therefore, if we have a large value for K for our rate constant or our activity, we have a short half-life. Small rate constant, long half-life. Here we can see the decrease in the number of carbon-14 nuclei versus time. Carbon-14 is a radioactive nucleus, and we can see carbon-14 decaying away over time. And you can see here is a long time scale, just arbitrarily 20,000 years. And you can see the half-life is constant. So 5,730 years between each half-life, the first half-life, then the first to the second to the third, and so forth. So at any point, the time for half the nuclei to decay away for carbon-14 is 5,730 years. Here we can see decay constants for beryllium, and you can see that beryllium has a series of different isotopes. One of them shown in the table is stable, but others have very different half-lives. And you can see the half-lives can vary from very short time scales. Beryllium-8 has a half-life that is on the order of 10 to the minus 17 seconds. It's much less than a femtosecond, all the way out to 10 to the 6th years for beryllium-10. So depending on the nucleus or the nuclide, you can have a very different half-life with a corresponding very different rate constant for decay. One of the applications that's very commonly discussed is radioisotope dating or radioisotope measurements. Radioisotope measurements can be used in biological processes for molecular biology and for biomedical sciences. We're not going to talk about those. Your book mentions a few. we're going to talk just briefly on radioisotope dating for dating very old objects or determining how old a structure is. And we're particularly going to look at carbon. This is one version of radioisotope measurements. There are a variety of different radioisotopes that can be used for dating. Radiocarbon dating looks at the relative amounts of carbon-14 to carbon-12 in materials that had a biological origin. So we know carbon-12 is stable, carbon-14 is not, and carbon-14 has that half-life of a little over 5,000 years. And we find out that the ratio of carbon-14 to carbon-12 is the same for all living organisms, approximately. Once the organism dies, the amount of carbon-14 begins to decrease. The amount of carbon-12 does not decrease, and carbon-14 decays to nitrogen-14. Since carbon-14 is decaying at a predictable rate, measuring the amount present indicates the time that has passed since the organism dies. So if we can get the ratio of carbon-14 to carbon-12, that ratio will decrease over time at a very predictable rate. Similarly, potassium-40 to argon-40 ratios can be used to determine the age of certain rocks. That's another type of radioisotope dating. So here you can see, ages of objects determined by radiocarbon dating. These are just some examples over the last 16,000 years. Various sorts of, kind of human or biological sites, and you can see that you've got your natural logarithm of your specific activity of your carbon-14 decreases over time for these various applications. Your book talks a little bit more about this. Now we're going to begin looking at nuclear transmutation. Nuclear transmutation is the induced conversion of a nucleus of one element into another. Now, we can think of this as being achieved by high-energy bombardment, but as we saw earlier, when red giants explode leaving behind a neutron star, there's large releases of neutrons, and you can actually have induced conversion, and that's how we get our heavier elements. But humans can do this as well. And we can do this with high energy bombardment of nuclei and what we call a particle accelerator. So for example, we can take nitrogen-14, bombard it with alpha particles, and produce oxygen-17 with a proton being released. Nuclear transmutation reactions can be described using a specific shorthand notation. This is kind of their version of a chemical reaction. This is a nuclear reaction, so you'll write reactant nucleus, and in parentheses you'll write particle in, comma, particle out, close parentheses, and then the product nucleus. So for our nitrogen-14 reaction we just looked at, we can write down nitrogen-14, parentheses, alpha, which is the alpha particle with which we bombarded the nucleus, comma, proton, which is released in the process, and our product is O17. There are a couple of types of different accelerators. One is called a linear accelerator. In a linear accelerator, you take your initial particle source. It could be an alpha particle, or it could be a proton, or it could be other particle, and beta particle, and you do an alternating voltage. So you basically attract the proton to electrode 1, and then you switch the voltage on electrode 1 to repel it into electrode 2, which is now attractive. And then after it's passed through electrode 2, you switch that voltage and make electrode 3 active, and so forth. And you can accelerate particles up to very high speeds. This is typically done in a large evacuated tunnel, so that there's no gas to collide with. So these particles can pick up speeds that can approach a relativistic speed. They can approach the speed of light, and at the end, you'll have a target that you'll crash into. So linear accelerators, for example, up in Northern California, there's something called the SLAC, the Stanford Linear Accelerator. And below are what we call cyclotron accelerators. These allow us to take things up to higher speed and occupy a smaller footprint. You can basically accelerate your particle faster and faster in a circular motion using electric and magnetic fields. This is what's called a cyclotron accelerator. And for example, there are examples of cyclotron accelerators throughout the U.S. and in Brookhaven and Argonne. So here are some transuranium nuclides, that is, nuclei that we've made on Earth, which don't occur naturally. Americium, curium, berkelium, mendelevium, and so forth. And you can see the half-life of the various products. They all tend to be relatively short. These are very large nuclei that tend to be pretty unstable. And in these processes, we see that there's an interconversion of mass and energy. So this takes us back to all the way back to our earliest discussion this year. So we started off with some ideas about conservation of mass and conservation of energy. So we say in any chemical process, mass is always conserved. But as we found over the years, that it turns out mass is not conserved, but mass energy is conserved. So physicists have kind of discovered this more broad conservation law. The total mass energy of the universe is a constant. Reactions that release or absorb energy also lose or gain mass. And the relationship is tied together through this equation shown here, which is the change in energy in the system is equal to the change in mass times the speed of light squared. So you could see that we could rearrange this to get the change of mass, which would be equal to the change in energy divided by the speed of light squared. Thus, for chemical reactions, the change in energy is relatively small. So, if we're looking at things that are on the order of a few hundred to 1,000 kilojoules per mole, that delta E is extremely small, so that the mass change is not measurable. It's effectively negligible for every process that we observe. But in nuclear reactions, delta energy is very large, and so our delta mass can be easily measured. We can think of this in terms of what's called nuclear binding energy. So it turns out that if we take the mass of a nucleus, it's less than the sum of all the masses of the individual nucleons. Because when the nucleons come together to form the nucleus, they are a more stable system held together by the strong nuclear force. That's a very strong force. And so the mass decreases when the nucleons form, and the lost mass is released as energy. And conversely, energy is required to break a nucleus apart into its individual nucleons. The nucleon binding energy is equal to the energy to break 1 mole of nuclei of an element into its individual nucleons. And typically we're dealing with very large values now, so the units we'll use are something called electron volts, or even larger, like mega electron volts. Thus, the nucleus plus the nuclear binding energy gives us the mass of all our nucleons. Since the mass of the nucleus is less than the mass of separate nucleons, we have to add in the nuclear binding energy as an equivalent mass. And we find out this mass-energy relationship turned into terms that we can think of in chemical systems. One atomic mass unit, remember one atomic mass unit is, that's equal to 931 million electron volts. So we could write this as 931.5 mega electron volts. Now, we haven't used electron volts or mega electron volts this semester. If we convert it into our familiar units of kilojoules per mole, one atomic mass unit is approximately 90 billion kilojoules per mole. It's a truly huge value. What we find is there's a variation in binding energy for the different types of nucleons. So as we pull our nucleons together to make our nuclides, we find what we can do is we can plot that binding energy per nucleon for our various nuclides. And we find that there's a peak in the binding energy per nucleon. And that gives us our most stable nuclide. So we see that the greater the binding energy per nucleon, the more stable the nuclide. And in this case, our most stable nuclides are pretty close to iron and nickel. Those are the most stable nuclei per nucleon. And ones that are lower in mass number tend to combine by fusion to form more stable nuclides. And those that are larger, of course, they tend to spontaneously fall apart by a process we'll call fission in a moment. So fission or fusion. Binding energy per nucleon peaks at elements with mass numbers near to 60. That is, near to iron, nickel, and cobalt. Nuclides become more stable up to approximately 60 nucleons. After that, the stability tends to decrease. And there are two ways that nuclides can increase their binding energy per nucleon. So the heavier nuclides, of course, they have lower stability, so they have to become smaller, and these split into lighter nuclides via a process called fission. So fission is when a heavy nucleus breaks into two smaller nuclei. Lighter nuclides will combine together to form more stable systems that have a higher binding energy per nucleon via a process called fusion. So when two nuclei come together to form a heavier nucleus, that is fusion. Here we'll look at nuclear fission. This is the splitting of larger nuclei into smaller nuclei. Typically, this is done using neutron bombardment to initiate the process. So that kind of gets us over our activation energy, if you will. Fission releases energy, and in that fission process, of course, we're going to smaller systems, so we don't need as many neutrons to hold the nuclei together. So we release these neutrons, and these neutrons can then go on to cause further fission processes to occur. And fission then, if we have enough neutrons, becomes self-sustaining by a chain reaction. And the mass that we need to achieve this self-sustaining fission process is called the critical mass. So the energy from nuclear fission then can be harnessed in a couple of different ways that we'll look at in a second, and converted into other forms of more usable energy. So we take these very high energies, down convert them to things that we can use more readily in our households and businesses. And here are a couple of ways. Now, the first one does not down convert readily. This is the atomic bomb, and it's based on uranium-235. An atomic bomb is an uncontrolled chain reaction where you launch together two pieces of uranium-235 at high speed to create your critical mass. When the critical mass is created, the nuclei begin undergoing fission. More neutrons are released, and the fission process accelerates until there's an uncontrolled explosion. It can be carried out in a controlled process called a light water nuclear reactor. And nuclear energy harnesses fission in a controlled manner. Typically, we carry out nuclear fission, and then the heat released by this is used to drive turbines and ultimately produce electrical energy. Nuclear reactors have a lot of potential in the future because there are no carbon emissions from these systems. So they would not be involved, for example, in human-induced climate change. Finally, we'll look at the nuclear fusion process. Fusion is where we bring two nuclei together at very high speeds to overcome the electrostatic force and then get into the strong nuclear force region where the nucleons hold together to form a new nucleus. An example is shown here where we take deuterium and tritium, collide these together at high speed to form helium, and when the helium forms, we have a neutron produced. The reaction shown here produces 1.7 times 10 to the 9th kilojoules per mole with no radioactive byproducts. And you can see that's a huge amount of energy. However, fusion requires a very large initial energy to get over the activation barrier to bring the two positively charged nuclei together. So this has not been done on scale to produce energy for folks. But there are two major research approaches that are currently taken to try and harness this fusion process to produce energy for people. And the first approach is to use a high temperature gaseous plasma that's contained inside a magnetic field. It's something called a tokamak, and we'll look at that in a moment. And the other approach is to use a series of pulse neodymium YAG lasers all blasting down together at the same time to compress and heat the fusion reactants to cause the fusion process. Now, of course, it's worth noting here that for fusion, we're producing neutrons, and of course, those neutrons can go on and do neutron activation and damage the surrounding structures. But there are, of course, thoughts that one could use water to capture the neutrons and produce more deuterium and more tritium. So there are theoretical ways of approaching this, but this is still a ways down the road. So we can see here on our slide, the first one is the tokamak. We have a magnetic field, and so we contain a plasma inside this magnetic field, which we can accelerate to extremely high velocities to create our nuclear-induced fusion. So we can induce a fusion process inside this plasma, but the tokamak has not reached, even on a research scale, has not reached energy neutral yet. Below here is the National Ignition Facility. This is located in Northern California, where the neodymium YAG laser array is built. And you may recall this from back in the fall. There was a press release where they had carried out laser-initiated fusion, and during they were able to get more energy out than they put in during a particular experiment. And of course, that's a key place. Ultimately, you need to get more energy out than you put in. You need to get a lot more energy out than you put in if you're going to create a power plant from this. But there's still a lot of technological barriers to overcome. So, questions still remain whether to use fission or fusion as a supplemental energy source to power humankind. So that completes our videos for this semester. And now you can continue on with your work.